Hello everyone, my name is Mr. Minnick. Today's lesson about Algebra 2 deals with Chapter 5, Section 7, and it's called the Binomial Theorem. The Binomial Theorem. A lot of times people want to make up their own rules. Well, in math, when we have rules that are in place, they're ideas that somebody has that could be proven, and usually they're called theorems. So sometimes people want to try to foil something like this. They want to foil something like a plus b times a plus b. If they foil that, they're going to foil it right. But if it were written as a plus b, the quantity to the second power, if they tried that, chances are they're going to make up their own rule that's going to be wrong. Because what they're going to try to do is something like this, and this is wrong, so don't write this down, but they're going to say, okay, so I need to distribute the second power to the a, so I'm going to get a squared. And I need to distribute the second power to the b, and I'm going to get b squared. Well, if it were a Meatloaf song, they'd be doing okay, because Meatloaf in one of his songs says 2 out of 3 ain't bad. The right way to have expanded this would be to take a plus b times the quantity a plus b, and foil it. And when you foil it, you do get a squared. So again, a squared is part of it. The last term is the b squared. Okay, so 2 out of 3 ain't bad. Why'd you leave room in the middle? Well, because in the middle, the inner product of foiling gives us ba, otherwise known as ab, because of the commutative property. Okay, the outer product also gives us a times b. Well, we have one a times b and another a times b. When we put the two together in the middle we get plus 2ab, which is not in that errant or wrong way of doing this, okay? So you might say, okay, so what's this binomial theorem all about? Well, the binomial theorem lets us expand something like this. A plus b to the third. Now you're probably thinking, well, I could foil it and then distribute again, and you could. Let's see how that would look. So it would be a plus b times a plus b times a plus b. And we saw a minute ago that from this product, why did I pick those? Just because that's how I did, okay? From that product, we're going to get a squared plus in the middle is 2ab, remember, plus b squared, okay? So it would be that multiplied by a plus b. And you're thinking, well, that's not so bad. We just distribute. Yeah, it's not. So when we distribute out front, we're going to get an a cubed, okay? On the end, we're going to get a b cubed, okay? Now, as far as what happens in the middle, it's kind of tricky. We're going to have a squared b. We're going to have a squared b. And then we're also going to get another a squared b from that product. So we're going to get, actually, we're going to get two more a squared b's. So that what that's going to give us is plus 3a squared b. Okay, I told you this part's kind of tricky. And then we're going to get ab squared on that outer product. I don't know if you can see that. We're going to get an ab squared, and then when we multiply b times the 2ab, that's going to give us two more ab squareds. So what that means is we're going to get plus 3ab squareds, okay? And you might be thinking, well, okay, well, that wasn't so bad. Well, yeah, you're right, it wasn't. But what if we wanted to go with a plus b, the quantity to the 7th power? That's going to take some time, a lot more time than most people have on their hands. So that's why we have the binomial theorem, and the binomial theorem is pretty scary. It goes like this. It says, a plus b to the nth power is defined in the following way. You might want to write small for this. You may want to turn your notebook so that it's landscape rather than portrait, because it goes like this. Subscript n, capital C, subscript 0. So that's subscript n, capital C, subscript 0. That's a combination of n items, and you're choosing none of them. a to the n, b to the 0 plus. Now, that's just the first of many terms to follow. How many? Well, it depends. So in the binomial theorem, this altogether is the first term. To be clear, NC0 is the first coefficient of the first term. And to be even more clear about this b sub 0, or b to the exponent 0, that's actually going to equal 1. And essentially, it's just going to go away. So some textbooks will leave that out. Okay, so let me continue. Plus NC1, so that's subscript n, capital C, subscript 1, NC1, a to the n minus 1, b to the first. Okay, so to be clear, this whole thing right here comprises our second term. Okay, and again, to be clear about things, NC1, that's a coefficient. That's going to be a number before the second term. And we'll talk in a minute about where those numbers come from. One more time, to be clear, this exponent 1 really doesn't need to be written, so that's probably going to go away also. Okay. So continuing this pattern, then our next term would be NC2. By now you probably are starting to see a pattern here. A to the power n minus 2, b to the power 2 this time. So again, to highlight some things, NC2, that's a coefficient. Let me get my box going the right way. Okay, so the whole next term is all of this stuff. Okay, I'll get my highlighter again. NC2, that's a coefficient. That's going to be just a number. And both terms, like the A and the B, nothing's going to cancel there, okay? So now that you get an idea how this pattern goes, I'm going to put a plus, dot, dot, dot. I told you you want to leave some room because it keeps on going. I'm going to actually have to extend this a line below. I'm going to jump all the way to the end, the last term, and you might be able to see what's going to happen in the last term. Okay? In the last term, its coefficient is going to be NCN, and we're going to have a to the 0, b to the n. Okay? So again, to continue how I had been doing before, this is the last term. Okay? To make things clear, NCN, that's the coefficient of the last term. And this a to the exponent 0, that's really going to equal 1, and that's going to drop out. And a lot of textbooks, again, will leave that out. Okay? So the term before that, the term in front of that, will be as follows, plus NC n minus 1, a to the first, b to the n minus 1. Okay, so let me see if I can get my little box here around that. See if the smartboard likes me today. Okay, so again, everything I'm highlighting in yellow here is simply a number. It's going to be a coefficient. Okay, and that was supposed to be yellow, not blue. So let me get that highlighting out of there. And actually, anything I'm highlighting in that blue color is basically not going to be written because it doesn't need to be written. Okay, because it's going to simplify a little bit. So again, that's a coefficient. And we'll do one more term before that. The term before that will be NC n minus 2, a squared, b to the n minus 2. Okay, so one more time finishing this sequence out. The coefficient is this NC n minus 2, and that's what the binomial theorem says. It in effect tells us how to expand a binomial of two terms, because that's what a binomial is. It's a polynomial of two terms. How to expand one to any power that we want to. The first, the second, the third, the fourth. It should be noted we're going to raise this to some kind of positive integer power or natural number. That's why we use n for the exponent there. Okay. So, might not be pretty, but that's the binomial theorem. So, a couple things about it that you need to know. First of all, you're probably wondering, what's this NC whatever crap? Well, there's a formula that says it's n divided by n minus r, r. What the heck does that mean? You don't even need to know what that means, okay? We'll study that in an upcoming chapter, in an upcoming section. You should know that n factorial is n times n minus 1 times n minus 2 times dot, 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 all the way down to times 1. It's called a factorial notation. So a specific case of that would be 5 factorial is 5 times 4 times 3 times 2 times 1, or 120. But you don't need to know that, because those combinations can actually be found using something that a guy by the name of Blaise, what a name, huh? Blaise Pascal came up with this ingenious idea. The only thing that's weird about it is the top row is the 0th row, okay? So row 0 of this triangle that he has a 1 right in it, okay? Now if we go to row 1 of this triangle that he has, if we go to row 1, it's going to have a 1 and a 1, kind of staggered a little bit. And if we go to row 2, you'll see a 1 and a 2 and a 1. Now at this point you might think, well, that's weird, it's a triangle. Yeah, it's a triangle. It keeps on going. Yeah, it keeps on going. And there's a lot of patterns that emerge. Such as what? Such as the fact that along this outer diagonal and along this outer diagonal there will always be the number 1. In subsequent rows, the next number will be whatever number of the row that we're in. Now remember, at the top it's row 0. So if we go to the next row, the row 3, what's going to happen? We're going to have a 1 and a 1. And then you might say, well, what goes in the middle? Well, there's going to be a 3 here, and then there's going to be a 3 here. And you might say, well, but I don't get it. What's going on? Well, you'll see in a minute. You'll see in a minute. Okay, let's continue this out a little bit further. Row 4 is going to have a 1 in it, and a 4, and a 6, and a 4, and a 1. Okay? So maybe you start to see what happens. The second number in is always going to be whatever row we're in. So if we're in the 5th row, the second number in is going to be a 5. And then to get the number after that, yeah, it's kind of like a Fibonacci sequence in a way, because in a Fibonacci sequence, the next term is the result of adding the previous 2. So what I'm saying is, not the previous 2, the 2 above it. What I'm saying is, if we look at 3 plus 3, 3 plus 3 is kind of where this 6 comes from right here. Okay? And if we were to have slid over this 1 plus the 3, the 1 plus the 3, that's where that 4 comes from. Okay? So let's think about what row 5 is going to look like. Row 5. Okay, row 5 is going to have a 1 in it, and a 1 in it. So to continue this idea, we're going to take, well, we said it's going to have a 5 next, right? 1 plus 4 gives us the 5. And then 4 plus 6 would give us 10, right? Moving to the other side of that, 6 plus 4 also gives us 10. And then 4 plus the 1 gives us a 5. So that's what the 5th row of this looks like. And I do have a picture of this hanging in my room. You've probably seen it. So if we continue to row 6 then, if we continue this to row 6, we've got a 1 and a 6 and a 15 and a 20 and a 15 and a 6 and a 1. So one thing to notice about Pascal's triangle is this. Some of the rows have a double term in the middle, and some of them just have a single term in the middle. Some people maybe want to memorize that all the odd ones have the double term in the middle, the even ones have a single term in the middle. I've never really worried about memorizing it. Once you get the first 3 rows, you can actually build this triangle on your own pretty easily. Okay, so that's Pascal's triangle. What's going to happen in a minute is we're going to try to apply this and see what we're talking about. Okay. So the cool thing about Pascal's triangle is this. It talks to us. It tells us some things. That 1 right there is actually 6 choose 0. Also, this 6 right here is actually 6 choose 1. Also, this 15 right here is 6 choose 2. And this 20 right here is 6 choose 3. And so on. So what I'm saying is if you go back and you look at the binomial theorem and you're trying to figure out how am I going to come up with all those numbers simply come from Pascal's triangle. So you don't need to worry about using this formula. Okay? So in a minute, we're going to try an example or 2 or 3 live, and we're going to come up with all these coefficients and all that. So anyway, hopefully you're intrigued and you're ready to try an example so that you can figure out how the homework goes.